Hello and welcome to Programming Like It's 1979, NAND to Tetris. Today we're going to start the CPU lab. This is probably going to be the longest lab of the hardware portion of the course. We're going to build some memory and a CPU, and then we're going to put it all together into a computer. So let's jump right in. All of the exercises for this assignment are in the Projects 05 directory of your NAND to Tetris installation. So we're going to look at memory.hdl. Now, some of you might be asking, what gives? I thought we made memory last week. Well, we made memory chips last week, but now we have to make a system memory module that includes both the RAM chips we used, but also maps memory to the screen and keyboard, specifically so that we can read and write to and from the screen, and so that we could write to the keyboard. So, right off the bat, what do we have here? We have a very detailed description that I'm not going to read. I am, however, going to make the font a little bigger here so you can read it, possibly. And then write, this is basically saying a write will happen on the subsequent cycle, whereas reads happen immediately. Okay, we have this load bit, which we've seen in a lot of our memory projects so far. Now, this is the meat of the issue. Only the upper 16K plus 8K plus 1 words are used. Access to any address in the range 4000 to 5FFF results in accessing the screen memory. Access to 6000 results in accessing the keyboard, 6000 hex. So if we pop some of these values into a programmer's calculator, so let's see. So 4000 means the 14th bit. No, the 15th bit. It's bit 15 in position 14 is a 1 and everything else is 0. And then we've got this 5FFF. Let's look at that. Let's actually do this right. 5FFF. And looking at this 14th and 15th bit, we see they're 1, 0. So those are the things we're going to need to distinguish on, is these two bits. So we're going to need some flavor of mux, and the question is, what size mux are we going to need? While we think about that, let's do what I always like to do, which is to build these devices from the inside out. So what are we connecting to here? Well, the hint is right here, 16K plus 8K plus 1. So we actually built a RAM 16K module, so let's place that. We know we're going to need RAM. And we're told we're going to need a screen, right? Right up there. Screen memory. That is a provided part. We don't have to build the screen, thank goodness. Grab that chip. And we also need the keyboard chip. So what do we have here? Well, right off the bat, the interface for our keyboard is very simple. It just comprises an output. So let's go ahead and create a net, as they say. I like to think of it as just giving it a name. We're taking a wire and we're giving it a name. You know, we don't even have to say keyboard out. We'll just say keyboard. All right, let's do the same for the screen. And let's do the same for RAM. If load is 1, then the in value is loaded and the memory location specified into the memory location specified by the address. All right, so your instinct might be, well, that says load and that says load, so maybe I should just do that. I believe that that instinct is probably wrong based on when we built our RAM. If you recall, when we built our banks of RAM, we ended up doing this trick where what we were demuxing in was essentially, where's this load bit getting shuffled off to? And so rather than sending data memory through the demux, the thing labeled here is in, we would always wire the data memory to our RAM chips, and then the load was the thing we were actually routing via the demux. And I think that's probably true here. So we know we're going to need a demux, so I'm going to call this demux out. I'm positing the existence of some wire, demux out, that we have not yet created. And following that instinct, I'm going to go ahead and do this as well. Although I'm less certain about this, but let's see if this works out. And this address here is kind of the question. And the reason that's the question is I don't think the size of this address is quite known yet. All right, so what are we going to need? We're going to need some sort of demux, and we're going to need some sort of mux on the other end. So what does the demux look like here? Well, I don't think the demux is going to work, and the reason is we have 3 possible destinations, and demux only gives us 2, A and B. So right off the bat, it's going to be either the 4-way or the 8-way demux. Let's try the 4-way for right now. So what are we routing? As I said, I believe we're routing this load value. What is the selector? Well, if you'll recall, bringing back our calculator, I think the selector is actually this bit right here, because if it's 5 FFF, we've got that, and if it's 6000, oh, you know what? Maybe not. Okay, I think I see. So this value, actually the critical point here is the rollover from 3 FFF to 4000, because that's the point at which bit 15 here, which is going to be address 14, rolls over from 0 to 1. So if address 14 is 0, right, so we need bits 14 and 15, is that right? No, it has to be 13 and 14, I think, with 14 being the most significant bit. Well, let's see how that works. So if the first bit is 0, that's these 2 cases in the demux, then it's going to go to there, right? I think that's correct. In either case, it's going to go there. Right, so we've chopped off this first bit, and so therefore it's the second one. And so C is going to go to our screen. I said RAM out, that's wrong. It's a new wire. We're going to call it RAM in. Screen in, and we'll call this keyboard in. Let's make this keyboard out. I'm changing my mind. All right, I think that may be correct. So then that brings us back to here. Right, we're loading that. That's coming in here. And what I've done here won't work, because I'm essentially saying take these 2 wires coming out of... Will that work? I think this actually won't work, because this is like a loop in the circuit. I'm trying to do an implicit OR here, so I might need an OR gate to wire these 2 together. But let's see what happens if I leave it that way. I might be wrong. And then this is going to get screen in, And this, actually, there is nothing going into the keyboard, so this is wrong. So that just needs to be null, which means leave the wire unconnected. All right. So what's happening here is the demux has basically consumed the 14th and 15th bits of this address. So everything less than that is getting passed on. So we're going to say address 0 through 12. And that's going to be the same thing here. All right, so that's the loading portion of this. And then we also have these outputs coming out that somehow need to be wired to this output. So let's go ahead and we're going to almost exactly mirror this on the other side. So A and B are both going to be wired to our RAM. C is going to be wired to our screen. And D is going to be wired to our keyboard. Out is just going to out. And what is the selector for this? Again, it's going to be that. So I think this is almost correct. The one wrinkle here is, as I said, I'm uncertain if this is a valid layout. I might need a gate to make these work. So let's load it into our hardware simulator and see if it even loads. If it's not valid, I expect it to complain on load. Yes, there we go. An internal pin may only be fed once by a parts output pin. Well, I expected that. So how are we going to do that? We're going to, let's just call it RAM A, RAM B, and we'll put an OR gate here. Put it here. This is getting RAM A. This is getting RAM B. And this is going to be RAM N. Try it again. Now we have a different error. Address 14 and address 13 have different bus widths. Line 34. Which line 34? That's here. So clearly this is not the correct bus width. Right, so as we look at the RAM, we can see the RAM address field, address input is 14 bits wide. And if we look at this, we're passing on 13 bits. And that makes sense because the RAM itself is a compound chip and it's going to consume that top bit. That bit 13 that we used here in the demux is also going to be consumed by the RAM to decide which bank of memory to switch this to. So I think changing that to 0 to 13, is that true of the screen as well? I don't think so, because the screen is just 8K. All right, back to our simulator again. Let's see what other mistakes we made. Line 40, scren in. Well, that looks like just a typo. You all probably saw that typo long before. You've probably been staring at that saying scren in for 10 minutes. Jumping up and down and shouting at YouTube, find the typo, fix it, it's driving me mad. There we go. So now this loaded. Let's load our test, which is going to be memory.tst. Before you run the script, select the screen option from the what? I can't read it. All right, let's choose view. I think it's view is probably what they want to see. We'll put it in hexadecimal. Make it as fast as we can go. Click on the keyboard icon and hold down the K key. There we go. Make sure you see only 2 horizontal lines in the middle of the screen. 2 horizontal lines, hold down Y. Comparison ended successfully. That's wonderful. All right, and with that, we are ready to start building our CPU. We've got a nice blank canvas here in digital. Let's look at the definition of the CPU. So this is pretty complicated, and I'm not going to read it all because that doesn't make compelling YouTube. You should absolutely be looking at the book and trying to understand this stuff. But what I'm going to do today is I am going to try to draw this CPU. I'm going to try and actually design this in digital visually, and then we will take our visual representation and turn it into HDL. Sometimes I think visually, sometimes I think in code. I think the first time I did this project, I actually did it in code first. So don't feel like, don't feel bad if you prefer one way to another. But I like the idea of trying to lay this CPU out. So today I'm going to start with, I don't even know if we're going to get past this since this is so complicated. I'm going to start with placing the parts that we know we're going to need beyond a shadow of a doubt, and then starting to deal with the inputs and outputs and ask ourselves, what pre-processing or post-processing are we going to need to do to deal with all of these? So what we know from the description is that we're going to use our ALU that we built last time, and we know that there are 2 CPU resident registers, the D and A registers. And then there's going to be some memory, which is our memory module that we literally just made. And in fact, this could be something that gets in our way because we're not going to have... No, that's fine. We don't need this as a chip in our design because it's simply going to be a conduit, an output leading to memory. Okay, so we know we're going to need an ALU and 2 registers. Let's go here. We should have some custom components here. There's our ALU. And you could see it's labeled all of our components. That's nice. And we need our registers. Oh, but we don't have... I don't think we graph the registers. Let's see. We can use these as temporary targets. And if these aren't what we need, we'll worry about that later. Okay. Can we name these? We can. How nice. All right. I don't know where we're going to want these living or how we're going to lay out the rest of our code. We'll just put those there for right now. Now let's go look at our inputs. What have we got? We have 2 16-bit inputs and 1 1-bit input. In M, which is the contents of RAM, and then our instruction. And not to spoil the surprise, the instruction is going to be where a lot of our complexity lives. All right, so we need inputs. Okay, this is going to be a 16-bit input labeled in M. We're going to duplicate that, put it here as our instruction. Already off the screen. That's going to happen a lot today, I promise. And then we need a 1-bit input. It's going to be our reset button. Let's look at our outputs. We've got an output going to memory, which is 16 bits. An address output and a program counter, which are each 15 bits, and a 1-bit value indicating whether we write to memory. All right, so let's place some outputs. So I think we said this is going to be out M. Let's do these in the order in which they gave them to us. This is going to be write M. And then we've got our 15-bit outputs. Address M. Is that right? I think so. And then we've got, I'm going to put this here for reasons. $15 bits PC. All right. So the interesting thing here is if you look at the ALU, you can see it's got all of these inputs. And these two, X and Y, are multi-bit inputs. I believe they're 15 bits. But ZX, NX, ZY, NY, F, NO are all 1-bit flags. And in fact, as you may remember from our machine language the hard way video, these flags actually all correspond to bits in our instruction. So these are coming off here. We can't really use this we don't want to use this as a 16-bit value. What we want is to break it out such that these bits lead to different places. So let's go ahead and drop a splitter. Where are those? Those are under wires, I think. Yep, splitter merger. Put it there. So how much do we want to split this is the question, right? Oh, someone actually gave me a great tip, which is that this spreading value here will adjust how much space you have in between each value, I think. So let's go ahead and say our input is going to be 15 bits, I believe we said. Was it 15 or 16? It was 16. Okay, so 16 bits. And let's go for broke. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Wow, we got a lot of spreading there, didn't we? I guess it's my fault. I configured it. All right, we'll leave that like this for now. All right, so this is going to be our most significant bit. And this is going to be our least significant bit. So what does this look like? Well, we know that these 3, 0, 1, and 2 are our jump flags. 3, 4, and 5 are our destination flags, which means bits 6 through 11, and arguably 12, but 6 through 11 really are going to be our inputs to our ALU. So one thing we could do is we could just start drawing wires here and wiring them up. But there's another argument here, which is if we connect these all to nets, then we can have a much neater layout and just pull these control bits out where we need them. And so I'm going to actually do this that way. So let's pull up the description of the opcodes from chapter 4, remember, not chapter 5, of NAND to Tetris, and start placing some nets. This is going to be, I'm going to start all these with a lowercase c. A or C. I'll say type. 14 and 13 are unused. 12 indicates whether this is going to be an A, whether the A register is going to be direct or indirect. All right, and actually the order is the same order in which these flags appear on this chip by luck. So this ZX is bit 12, bit 11, 10, 9, 8, 7. Grab another tunnel. And lastly, but not leastly, our negate, C-N-O, negate output. All right, so now we have these defined, right? So what we can do is, rather than pulling the wires across, we can simply drag them over here. Same thing here. We're just going to do this all the way down. And that is actually, that actually handles a surprising amount of the complexity of our CPU. And this is something which is conceptually very simple, but if you're actually drawing all these wires, they really get in the way. And so now we've just eliminated that with a few well-placed tunnels. And I'm going to go ahead and place tunnels for all the rest of these things. We're not going to use them right away, but we will need them sooner or later. Just going to go ahead and put these down. You know what? I'm going to put them all down and then name them later. So these three are the jump flags. And I believe, if I recall the documentation correctly, we've got jump greater than, and jump equal, and jump less than. I'm just going to name those as if they're machine language or assembly language opcodes. Just as a mnemonic for me, if you have a different mnemonic that works better for you, you should go ahead and use that instead. Then our next three bits are our destination bits for memory. And the order in which these are defined, bit 3 is M. So let's say, call it dest_m. It's MDA. Bit 4 is destination D. And bit 5 is destination A. Okay, that goes there. That is all of our flags, I think. So we haven't, many of these are still not connected to anything useful, but they're at least primed and ready to go for us to put nets elsewhere and figure out where they're going to be wired up to. So I'm actually missing a part that I need to graph this. I was thinking, let's do this reset button and wire it up to the program counter. That'll be easy. But I confused myself because this PC here is not a conduit to the program counter chip. This is actually just the 14-bit value or 15-bit value that is the program counter. So we actually need a program counter chip to have somewhere to wire this up to. So I'm going to have to make that program counter chip. I don't know that it's interesting at this point to watch me graph it. We made it in HDL last week. So I'm just going to go off and make it, and I'll be back in a moment with a completed program counter chip. Okay, we're back, and we have a simple incrementer and program counter. Let's try and place it. Look at that. Beautiful. We now have a program counter. All right, so what can we do here? We know that this reset button is going to be wired up to that program counter input, which is also called reset. All right, now we're still going to have to do more with the program counter here, but we can do that as we get to it. Okay, so now if we think of the three areas of the CPU we've talked about, on the left-hand side of our screen, we've got roughly the instruction decoding parts. And there's not a lot here yet other than our tunnels, but we'll be adding more as we go on. On the right-hand side, we've got our outputs and our jump logic. Our jump logic is going to go here because what jumping is going to do is it's going to change the program counter. It's going to change it from being just +1 to whatever we decide it should be. And then we have our core CPU logic over here. So right now, as we look at this, as we look at what needs to be done, the thing that really jumps out to me are these registers. These registers are central to the operation of the CPU, but they're not connected to anything. And right now, there's not a lot of indications as to what they should be connected to. So how do you know how to wire up these registers? Well, in chapter 5 of the book, there is a block diagram that's sort of a very direct hint that gives you a schematic view of the core of the CPU without showing the control bits. And I think that's how most people taking the course figure out how to do it. But I think it would be fun to try to intuit or deduce how these registers should be connected to the rest of the system. So let's do that. So the A register, we know because of this control bit, what I've called the A or M control bit. We know that the A register sometimes acts as a direct register and sometimes acts as an index into memory. So the A register is going to be more complicated. So let's start with the D register. Now, if you think about the opcodes, right? These control bits to the ALU are what we have to work with. We have these X and Y inputs to the ALU. We don't know at this point which of what needs to be going in there. So if we look at our diagram about the control bits, we actually have four very simple cases out of this list of cases. We've got 0 and 1, which don't require any inputs. Those just come from the ALU. But then we also have this D and A cases. And if we look at the control bits, these control bits, I will just assure you, are in the same visual order as they appear in our schematic. So if we look at D, we see we've got 0, 0, 1, 1, 0, 0. So what does that suggest? Well, that means that our ZX and NX flags will be off, and our ZY and NY flags will be on. So what does it mean for ZY and NY to be on? That implies that whatever value we put into the Y value here, we're going to first turn it to 0 and then negate it. So it's going to be essentially all ones. So that's sort of the moral equivalent of throwing it away, isn't it? And F being 0 means that we're going to be doing a logical AND. So that means that whatever value comes into X, we're going to be ANDing with Y, which is the same thing as give me back whatever I put into X. So since this is the opcode for D, this is essentially the identity opcode for whatever goes into X. And since we're being told by the documentation, the spec, that that's going to emit D, we now know that D goes into the X register. Excuse me, I didn't mean register, I meant input. Now, by the same logic, looking at the A mnemonic, we see we've got 1, 1, 0, 0, 0, 0, which is the exact same logic as the D opcode, simply with X and Y reversed. So X is going to be treated as an identity, or rather, X is going to be turned into all ones. We're going to AND with all ones, and therefore whatever goes into the Y input is what we're going to input. So we could put a tunnel here from the A register as well, but we're going to have to deal with this fact that this is actually this opcode handles two mnemonics. It might emit A, or it might cause the CPU to emit M. And that's going to depend on this C, A, or M flag. So how do we deal with that? Well, we know this is essentially a condition. So whenever we see conditions, we think of muxes. So let's grab a 16-bit two-way mux and see if that feels right to us. And let's go ahead and use tunnels for our A output too, just for convenience. Feels like I'm spending all my time making tunnels. I am. So this A or M is going to be I believe that what we want is we want this mux to emit A when this is false and M when it's true. I'm going to have to double check that, but I believe that's the case. When A equals 0 and when A equals 1, yes. All right, so we have now satisfied all the inputs to the ALU with the asterisk that we haven't yet started indexing memory. So this is starting to come together a little bit. But what about loading Y from memory if this A or M flag is set to M? Well, we're actually given that index to memory just as an input. So we can just wire that up like that. And now, at this point, we are actually satisfying all of the inputs to the ALU. So let's start thinking about the outputs. Let me go ahead and make a few tunnels just for convenience. And I'm going to make a little more room here for our registers. And not only that, but again, I'm going to make very heavy use of tunnels to keep the layout sensible. Okay, so the next bit of control logic I'd like to think about are these destination flags. These destination flags decide where the output of the ALU goes. If the destA flag is set, the ALU output goes to the A register. If D is set, it goes to the D register. And if M is set, it's going to go out to memory. Now, these flags are essentially a mask, so more than one can be set. So let's, as we did before, start with the D register because that's the simple one. Now, once again, we actually have a small problem in terms of drawing this, although not in terms of implementing the HDL, because the registers provided by digital don't have the load flag that our registers that we make for the class have. So we could use these and attach a mux and fake it that way, but I'm going to go off and magically create some registers that we can use that will more accurately represent what you're going to see in the HDL. You won't have to do this when doing your implementation because you actually made those registers last week. And now we have a tiny register that we can use in our CPU circuit. Let's go back to that, get rid of the app provided register and use our custom one. Look at how cute that is. All right. Actually, digital, I believe, does give you a way to customize the layout so we could have the load sticking on the bottom like a mux, but we're not going to do that right now. So our in to this D register is just going to be the output of the ALU, but whether or not that is loaded is going to be determined by this cDestD flag. So let's go ahead and grab a wire or grab a tunnel and name it appropriately. We are going to have to connect the clocks to these registers. I'll do that later. I'll probably do that as the last step before we actually start simulating this. Now the A register is similar, but we actually have a little more complicated scenario there. The reason the A register is more complicated is that we might have to load it from one of two places or because of one of two reasons. Let me put the correct register down there. Yes, we might load the A register because the cDestA flag is set, but we also might load it if this 15th bit tells us that the instruction is an A instruction. So there are two reasons to load the A register, and to make matters slightly more complicated, the value that we're going to load is different in each of those cases. If cDestA is set, then we're going to load this ALU out value into the A register. If this cType is set, then we're going to take basically the top 15 bits or the the top 15 bits from here and put it into the A register. So that's a little bit complicated. Let's see if we can think about how to put that together, or we could defer that logic to later. I think we should give it a go. Let me do my labels here because I forgot to do that. And I don't want to confuse myself. And let me make a little more room here once again. I told you it would happen again. All right. So let's make a new tunnel to represent our load state, which means that something is loading into the A register, and we don't know what yet. So let's call it load A. The nice thing about using tunnels rather than wires in this design, apart from the fact that it's slightly neater, is that there can be almost a one-to-one connection between the names you give your tunnels on the diagram and the nets you use when you write the HDL. So you're going to see all of these names again when it feels like several hours from now we actually start writing the HDL. All right. So let's go ahead and make even another tunnel here, and we'll call it AN. And the main reason I'm doing that, even though we could simply have the wires here, is this gives me a little more freedom to lay it out however I want to lay it out. All right, so load A is going to be true if either cDestA or cType is set. So I think it's, or cType, if cType is 1 rather. So I think it's reasonable to plop an OR gate down and use that as our kind of first approximation for this. This might prove to be wrong, but that's okay. We could always change it later. So if either cDestA or cType. If cType is 1, it's an A instruction. If have I got that right? No, actually I'm wrong, because the actual spec is that if cType is 1, it's a C instruction, and if it's 0, it's an A instruction. So we actually need a NOT gate here as well. Just put that there and drop a tunnel. Okay, so at this point, that should be load A. But that doesn't help us deciding what goes in. So we need to use this value if it's cDestD, and this whole value if this is 0. Well, I said the word if, and you know what happens whenever we say the word if, we reach for a mux. So let's go ahead and grab one. We'll just put it right there for now. Let's make it a 16-bit mux with 1 selector bit. Can we do this with 1 selector bit? I think we can. All right, logically, the output of this mux is going to be AN. And furthermore, AN only has to be correct when load A is set. Because if load A is not 1, then whatever this input is going to be completely ignored. So maybe that helps us a little bit. So what is this mux selecting on? Well, I think the easiest thing to do is to select on this cDestA flag simply because it's already set to the correct value. Or if it's set, we're going to come in here. So again, if it's set, we're going to be taking the ALU out value. And if it's not set, then we want this value here. I need to give myself, oh gosh, is this going to work? Yeah, there. I need to give myself just like one more space here. If it's not set, we want literally the value coming off of here. And I'm going to call it let's see. I'm going to call it A input. Now this is not strictly true because maybe it's a C input, but we're going to be ignoring it. Are we going to be? Yes, we're going to be ignoring it because, well, here, let me put it all together first, and then I will walk through in my head and make sure that I'm not completely making this up. A input comes in here. Let's assume that it is a C value, not a C instruction, not an A instruction. And let's further assume that cDestA is set. We're going to come, is not set. So it's not set. So we're going to take the C instruction. That becomes AN. That goes here. cDestA is not set. cType is not set either. Therefore, load A is false. Therefore, load is not set. Therefore, AN here is ignored. We've got this A input, AN. It's kind of bad naming, but I'm going to leave it for now. I think this this might be correct. This also might be wrong. I think this might be another opportunity once we actually simulate this or write the HDL and write the tests or run the tests. This might be another case where I get to give a great lecture about how making mistakes is how you become a better engineer. But I think this is right. Walking through the cases in my head, I think this covers them all. So, well, let's go on. At this point, the interesting thing here is now we've covered all of the input flags, all of the control bits, except for our jump bits and, yeah, and our output flags. So we're getting closer here. We are definitely approaching We're approaching done with the CPU. Unfortunately, we're also approaching about an hour of recording, and that's after I've edited out some of the longueurs. So I may cut the video here and finish this up in the second part of the video. This is frustrating to me because this is, at this point, starting to look, I don't want this to be a 3-part series. I'd really like to finish this in 2. I think the jump logic can be done in about 5 to 10 minutes. And then the rest of the flags and the outputs should be done similarly. And then writing the HDL. And writing the HDL will go fast because we will have the schematic that we can simply follow. So, but I do feel this has gotten pretty long, so I am going to cut it here. All right, we're going to take a break, and when we get back, we will finish the CPU diagram. This has been Programming Like It's 1979. Thanks for watching.